let's get started. So I hope everyone felt that the midterm was not so difficult, or rather I should say appropriate. If you had any problems submitting the midterm, let me know so we could work something out about that. Otherwise, I think we can move on. I will be grading the midterm, so over the next week or so, we will formulate an answer key and then grade the exams. If you are interested in, once the exams are posted, if you're interested, then we could give feedback. But at this point, we aren't going to give individual feedback unless asked for. So I hope that is okay. But the idea is that we're going to try to be pretty lenient, because I think you guys taken this exam 3 times now, so that's kind of a lot. But yeah, so today we are going to discuss the steel phase diagram a bit more, and kind of go from there. If anyone has any individual questions, please feel free to stop me, and we can discuss them. Okay, let me just get situated. Okay, so over here, here we have the steel phase diagram, so everyone can see. And what we have, so the phase diagram is composition on the x-axis and temperature on the y-axis. And our composition in this case is carbon and iron, right? And we're going from 0 to 6.7% carbon and iron, because above 6.7, the carbon no longer will, the carbon is no longer, miscible in the iron in the way that we're interested in. And above 6.7, we get cast iron, which is a high carbon steel, great for cooking, not so great for, building things with. And so in material science, when we're discussing steel, we're really below 6.7%. Now, we have a couple pure phases. We have, the alpha phase here, which we call ferrite. So it's called alpha or ferrite individually, like interchangeably. We have this delta phase here that we call austenite, and then, sorry, that's not delta, that's gamma, right? Okay, austenite. And then we have a liquid phase, if we heat everything up high enough, we get a liquid phase. And then up in this corner, we have the delta phase. But because that only exists at very high temperatures, oftentimes we don't form it. So what exists is the fact that these phases are stable at certain temperature ranges, right? But humans aren't stable at all temperature ranges, right? So we need to exist down here. We need to exist at room temperature. And so the idea is all the tricks we could do to, you know, all the tricks we can do to get these high temperature phases to exist at room temperature. Because if we can do that, then we open ourselves up to different crystal structures and different mechanical properties that we can use. So the idea is how do we do that? And the easiest way to do that is to control the cooling rate, right? So if you cool something very slowly, you know, like 1 degree per minute, right? Very, very slowly, you give every atom the chance to move to its desired energy state, right? So if I say, okay, you have like, you know, if I say you have 2 weeks to go to, you know, 2 weeks to go to the beach, right? You're going to take your time to get to the beach because you have all that time, right? And you'll get there, or when you get there, it'll be good. But if I say you have 20 minutes to get to the beach, right, you're going to scramble, you're going to drive crazy, you're going to be reckless, and it might not work out, right? Because it's just not a lot of time. The same thing exists with atoms and phases. So if you give atoms enough time, they will go to the thermodynamic state, rest state. But if you make atoms rush, oftentimes we can trap atoms in these higher energy states at room temperature. So one way we can get different microstructures is by the rate of cooling. Another way we can get different microstructures is by controlling the composition, right? So if we have very, very low amounts of carbon, like down here, we would only have this alpha ferrite phase. But if we exist anywhere else along this plot, we're going to have this alpha ferrite phase plus this Fe3C phase, and then we call this cementite, right? And so why would we want this? Well, cementite, like the name suggests, is very hard. You know, it's very strong, but it's very brittle. Ferrite, on the other hand, is much more ductile. Ferrite has a BCC structure, right? So it's ductile. It's more ductile than the ferrite. So if we can get these two phases to coexist together, then we might get the best of both worlds. We can get the ductility from the ferrite phase and the strength from the cementite phase. So the easiest way to do this, or the first way we will discuss, is if we do a eutectic transformation. So a eutectic transformation, in this case, would be along this, at this composition here. So we would heat our mixture up, form the austenite phase, right? And if we have the composition exactly right to hit this eutectic point, then as we cool the sample very slowly, we will go from a pure austenite phase to a mix of the ferrite and cementite phase. Now, how does this happen? I'm gonna so if this is our cross section, right, and we have and these are different. And this is a cross section of grains of austenite, right? They exist. And as we cross this eutectic point, what's going to happen is at the grain boundary here, we're going to have a localized region of, you know, a carbon-rich phase. So there's going to be there's just, you know, because of the random chance, there's going to be a little region where there's a little bit more carbon, and that will form cementite, right? and then carbon will begin to migrate to this region. Like, so you have a lot of carbon here and it's going to attract more carbon. So then around the cementite phase that's forming, you're going to have a carbon deficient region, right? Because all the carbon is going to this red spot. So then you're going to get this green spot here, right? Of a carbon deficient region. And then you're like, oh, well, now any carbon that is in this carbon deficient region is kind of like, well, why am I sticking around here? And then you'll get another red spot down here. So along the grain boundary, as we cross the temperature threshold into this alpha plus cementite domain, we're going to have a segregation occur where the carbon is going to diffuse. And why would the carbon move? Why is the carbon the thing that's moving here? Well, carbon is an interstitial, right? So it's not taking up the lattice spaces of iron. Carbon is small, right? So you have a small interstitial. So you have lots of positions for it to move. It's low energy for it to move. So the carbon is really going to be driving this transformation. And then, right? So a region of high carbon is going to appear surrounded by regions of low carbon and vice versa. And then they're going to just continue to grow through the whole membrane. And what we're going to get is we're going to get stripes of the repeating, high carbon cementite, low carbon ferrite, high carbon cementite, low carbon ferrite. And we're going to get these stripes. And when you get this striped microstructure, we call that perlite. Perlite, because when it's polished, it's shiny like a pearl. That's the idea. These names are very scientific, right? So, and a lot of times in the past, before we knew about atoms, we knew we could make these different structures, but we didn't know why. And so that's why it was a very special thing to get like shiny steel that looked like a pearl, and that's why it's called perlite. So if you look in the book here, in the book, they have a lot of cross-sectional images, and you can see the bands of the different, very clearly of the different types of these phases. So now we have this mixed microstructure of the high carbon content cementite and the low carbon content ferrite, right? And the cementite is hard, and the ferrite is malleable. So if we hit this point, we have a 50-50 ratio. That's cool. Well, we got it, right? 50-50 ratio. But is that the only ratio we want? And is that the only thing we can do? And obviously the answer is no. So So we discussed this eutectic transformation here. But if we would want to not have an equal ratio of ferrite and cementite, maybe there's another. What can we do? We can change the composition. So if we go to a hyper hypereutectoid point. So hyper means above the eutectoid point. And maybe we start here. What's going to happen? So this is our starting structure here. We have the austenite phase. And we're going to cross and cool our sample. And now we're in this region, this domain here, where we have austenite plus ferrite, right? This austenite plus ferrite phase. And so now ferrite will, austenite plus cementite, right? Cementite. So now the cementite phase will precipitate out. I believe we said that was the green. So I'm going to make this kind of right. So now we have these giant green cementite crystals that form as we exist in this phase, in this region of the phase diagram. And if we wanted to know the ratio between austenite and cementite, we could do the lever rule, right? So here's the lever rule. So we can compare this length to this length, right? To get a ratio of the two phases, where this length on the right corresponds to austenite, and this way on the left corresponds to cementite. So now as we approach, cooler temperatures, right? When we're here, we have this microstructure that is very different, right? This microstructure is, it's austenite plus cementite. And so when we go cool even more into this region of ferrite and cementite, what's going to happen? Well, the phase diagram says we should only have ferrite and cementite, right? But we have austenite and cementite. So the austenite is going to decompose or undergo a phase transformation, but these cementite crystals won't be affected because they are still thermodynamically stable, right? They're still allowed to exist. I mean, the atoms in there are like pretty much happy, So what will happen is the same type of phase transformation will occur for the eutectic point, but these cementite crystals will remain unchanged. So along the grain boundary, we're going to get regions of high carbon regions in green, low carbon regions in red. And then eventually these regions will grow and consume the whole structure. And we'll get something that looks like this. So what we have now is we have the same type of perlite phase, right? This layered alternating phase of low carbon ferrite, high carbon cementite. But we also have these cementite grains as well, these hard types of grains as well. And when we look at this looks very similar to precipitation hardening, right? So we precipitated out a phase, the cementite phase, and it was very we got these little grains, great. And then when we continue to walk the material to cool the material, we created this layered structure again, but with the ferrite crystals still intact. And in this way, we generate a material that will have a higher hardness, right? It'll be more hard because we have more of a hard phase present. Now, you can do the same exact thing for a hypoeutectoid. So a hypoeutectoid would be if you were below the eutectic point. And then you would, as you cool, first you would enter this domain. And in this domain, instead of precipitating out the cementite, you would precipitate out ferrite. And then as you continue to cool the structure, then you would get the pearlite phase surrounding the ferrite crystals instead of the cementite crystals. How does it, is that good? Does everyone understand this? Any questions? Think about it for a little bit. Yeah? Okay, cool. So this is just an example of how we can process, how changing processing conditions can alter the microstructure and then ultimately alter performance. So let me see. And this is chapter 9 in the book still. Phase diagrams. Okay, we last week I believe we talked about nucleation and growth, right? And we talked about surface energy versus volume energy and how that could nucleate or control nucleation of phases. Okay. Cool. So okay, cool. So I'm gonna erase the phase diagram. So what we just discussed was thermodynamics. What we just discussed was that certain phases are stable at different temperatures and compositions. And if, as we move along the phase diagram, we can be kind of smart and get different phases to be thermodynamically stable and ultimately exist in our world. Now that's cool. I like thermo, unpopular opinion. Thermodynamics is neat, but thermodynamics is just the what if. Like, would you want to do something? So thermodynamics is, the low energy state isn't being in class. The low energy state is going to the beach, right? But kinetics is how. Kinetics is how do people, how does a reaction progress? How does a reaction move? So kinetics is, so you could have something that is thermodynamically favorable, but kinetically impossible. And in that way, even though I would want to be at the beach, I also don't have a car, so I can't get to the beach, right? So even the thermodynamics say you want to exist in some state, if you don't have a pathway or a route to get there, you can't go there. And so in phase transformations, it's a lot of the same thing. In phase transformations, a lot of times atoms may want to exist in some state, but we control the pathway in order to allow them or not allow them to go there. So the example I used earlier was cooling rate, right? So if we cool something at a very slow rate, we allow the kinetics to play out as they want to. But if we cool at something so fast, then we freeze the atoms in place, and that is called quenching. So quenching is when you cool something very quickly in attempts to minimize diffusion. So you might have something that's very hot, and then you like the microstructure that exists at the elevated temperature, so you would dunk it in, liquid nitrogen to really freeze it very quickly. That's a common thing we do, but that's also like kind of like really expensive, and that actually might not be exactly what we want. We might just want to control the cooling rate. So those many different ways, and then this is kind of where money comes into things. We like to think that science exists, very theoretically, like, oh, like science, yay, like do. But no, science is influenced by money, and science is influenced by logistics all the time. So yeah, it might feel like scientifically easy to do this, but economically hard, right? So if we had to quench all of the steel used to build the Empire State Building, that's not possible, right? That's too much. Who's going to do that? No one has time for that, right? So oftentimes when we make these alloys, cooling is like turning the oven off and opening the door and letting it cool like a cake, right? Or we keep the oven on and turn it off. And that's a different cooling rate, and that's how we control cooling rate. And so how does that affect phase transformations? Well, it can by controlling the nucleation and growth. And that's kind of what we're going to try to get to today. So that's good. Okay, so first thing I want to do okay, so the first thing I'm going to do is I'm going to draw the graph from last week. So the graph from last week looks like this. And so this graph, what we have here is we have the surface area. Right, so we have the surface area interfacial energy. So as we grow a phase, we get a bigger surface area, and then there's a lattice mismatch between our new phase and the surrounding phase that increases the energy of the system. Down here we have the volume-free energy. So the volume-free energy states, though, that the new phase is thermodynamically favorable. So atoms have a lower energy state in that phase. So we have this competing force between the lower energy of the volume and the higher energy of the surface area, right? And so surface area is, to the power of 2, but volume is to the power of 3. So eventually the volume wins out and the overall energy of the system decreases. And that is dictated by this curve here. So this is delta G. Come on, monsters. This is delta G, which is the sum of the interfacial energy plus volume, right? And so for a new phase to form, the delta G, the Gibbs free energy of the system has to be negative, right? For the phase transfer to exist, it has to be negative. So this point here is the critical radius of the new phase at which it's more energetically favorable to be in the new phase than to be out of the new phase, and the new phase can exist. So this radius here is, the critical size, and this can change based on temperature, right? So this is affected by temperature. Let me just make sure I get this right. Okay, yeah, this changes on temperature. So higher temperatures will be like this, and lower temperatures would be like this. This is a high temp, low temp. Okay, so the lower temperature, at a lower temperature, there's less of a thermodynamic driving force. So it takes longer for the volume phase to overcome the interfacial energy phase. But at higher temperatures, there is more of a, the higher temperature, there's less of an interfacial energy differential because atoms are moving more. Like atoms are diffusing more, they're jumping around more. So to jump from phase 1 to phase 2 isn't as hard. So this surface area, the interfacial energy value is less. So as a result, what we can see though is that at different temperatures, the nucleation size will be different, right? So in other words, at different temperatures, it's going to take longer or shorter for a stable crystal to form. And what that looks like so I have time on the x-axis, right? And on the y-axis, I'm going to have percent phase conversion. I'm going to have percent phase conversion. And so what that means is, we're doing a phase transformation, and we're trying to track A to B over time. So when we start the experiment, we have all A, 100% A, right? We start the experiment, and then what we do is we wait, and it will cool, and we wait, and it cools, and it wait, and so eventually, what we're doing is we're waiting for some atoms to organize into the new crystal, to nucleate a crystal that is large enough that it's energetically favorable from the first graph. And it's large enough that can happen randomly, you know, as atoms, you know, randomly come together, but also as it cools, right? The radius gets smaller and smaller, and eventually it. Now let me see. As it cools, the in as it bleh, the radius doesn't, the critical radius doesn't change, but given enough time, a crystal will randomly appear of that size because atoms are randomly moving together, randomly colliding, right? So eventually we'll get something to form. And once that crystal is formed, once we nucleate that crystal, it will continue to grow. And new atoms would join it. And then eventually we will fully convert to 100%. Okay. This is temperature 1. So now we can repeat this experiment. We can repeat this experiment again at different temperatures and track how long it takes for a new crystal to form, or for this recrystallization to occur. And if we go to a higher temperature, what do we think is going to happen? If we go to a higher temperature, then atoms will be able to move faster, right? The interfacial energies will be less, and it will take less time for a new phase to nucleate and crystallization to occur. So if we go to a higher temperature, it might look like this. So we have T2 is greater than T1. And then if we go to a lower temperature, what's going to happen? Well, we're going to have to wait a lot longer because at lower temperatures, atoms diffuse slower and the crystal we need is larger. So at lower temperatures, and if we go to a temperature even lower than that, a temperature so low that diffusion basically doesn't occur at all, right? What's going to happen? We're going to wait forever and ever and ever. Right? We're going to be still waiting for diffusion to occur, for the atoms to grow to get to this huge crystal size where they're stable, and recrystallization or the phase change will never occur. So depending on the time at which we okay, cool. Okay, so the next thing we have to talk about are isothermal transformation diagrams. Right, so each one of these is an isotherm because what we do is we have a sample and we hold it at temperature 2. We have a sample, we hold it at temperature 1, temperature 3, and we track the conversion, or we track recrystallization, or we track the phenomenon, right? So these are isotherms. And these isotherms exist for A to B, right? A to B. But if we think of back to steel, right, and iron, there's ferrite, cementite, pearlite, austenite, amorphous, right? There's a lot of ites. So there's a lot of this phase diagram isn't as straightforward when we try to apply it to steel. So the next thing we're going to try to do is look at isothermal transformation diagrams for steel specifically. But I think, we only have 10 minutes left, and I don't think, I don't think, I want to take my time with it. So I want to go through it. So I think we are going to do that next week. Yeah. So yes, please, exam 1 grades, we are going to start grading them soon. So we will upload grades as we grade them, right? So hopefully your grades will come in. If you want to discuss your exam individually, I'll be more than happy to do that, and we can schedule a time to do so. I mean, it's your right, so please do that. Please take care of yourselves. Try not to do what I do and look at Twitter 24/7 about current events in the world. And if you need any help or any special considerations for your life, just email me and we can sort something out. So, okay, stay safe, everyone, and we will pick this up again next week. Okay, bye-bye.